Hello, this is Lecture 9 Highlights for Chem 1A by Joanna Castro. First, we have the nonmetals. As you can see in the little infographic to the right, we have the ionic bonding with metals and nonmetals, and covalent bonding with nonmetals and other nonmetals or metalloids. So, nonmetals form covalent bonds, and it's all about sharing, and they try to mimic the noble gases. The electrons that are shared are called, a bond, obviously, and the unshared ones are called lone pairs. Due to the duet octet rule, electrons have to have like 8 valence electrons. Atoms must have 8 valence electrons to be stable. Here we have hydrogen and chloride. So the hydrogen with its 1 electron would combine with the chloride to become a covalent bond. And to name them correctly, you take the two nonmetals that form their bond, and first goes the name of the element, then the second name of the other element with an ID at the end for "ide", and the order goes from left in the periodic table to right. And you can name them based on the number of atoms they have, on mono, di, tri, or tet. So for sulfuric, over here, on the right we have sulfur oxide. Because it has two oxygens, it ends in "ide" because it's the second atom, but also because it's the second two molecules or two atoms, so it's like di, like two, not the other word. But yeah, and there's also sulfur trioxide for 3 oxides present. Then we have multiple bonds. This just explains how bonds look like when you draw them. They can form single, double, or triple. Bonds are a pair of valence electrons, so 2 dots or 2 electrons would be 1 line. Here we have a single bond with hydrogen and carbon, 2 carbons forming a double bond, and also 2 carbons forming a triple bond. The formal charge is the correct or stable way to draw a Lewis structure based on its elements. So you try to make the formal charges equal to 0. You can't really see this infographic, but it shows H connected to nitrogen, carbon, nitrogen, and also another hydrogen. The one in the box with to the most right has them all even-ish, so that'd be the most correct one. But there are also other variations of how it would look, which would show a positive or a cation and anion, a positive and negative thing to it. That would be not, and some of them that's your only option. But always try to make it so that they're equal to 0. And I don't think I mentioned this I didn't put it down on the slides, but the element that has the most open valence electrons, like carbon for example, which has 4, would typically be in the center. As you can see the little examples. So carbon would be connected to nitrogen, and is that accurate? Well, carbon's typically the center for most of them. But anyway, nitrogen on the sides and then hydrogen to connect them to each. And then there's coordinate covalent bonding, typically with metals and nonmetals. Both try to dominate the shared electrons. That was typically provided by only one element. So here in atom A, we see that it has a pair of valence electrons that it's available for bonding, and then they combine with element B or atom B, and then they form a covalent bond. But also they're both fulfilled and are trying to go for the same set of electrons. It keeps them goodly bonded. It keeps them bonded. Anyway, resonance. This is one of the favorite. So this is when there are delocalized electrons. The compounds, while they're still the same, can be drawn differently. Here we have a ring of carbon with hydrogen on the outside, which you can form the carbon bonds to each, but also it's not strict, so they can be on either end. And a better way to draw this, if you were going to combine 2 of them, was to draw it like a circle, I guess, inside of an octet. And delocalized just means sharing electrons with across 2 or more atoms. And then allotropes are the different forms that a same element can take, oxygen and ozone. That's what they see. Anyway, here we see the double bonded, like in a double and a single bond, as like shown like the previous example slide. But this is like ozone is also a good example of resonance, as we can see like right above in like the middle image. We can see like it can be drawn both ways, like on either side, and both are technically correct. Lastly, we have bond length. The distance between bonded atoms, the smaller the length, the closer the atoms are held together. And double bonds are typically closer than a regular bond. For ozone, because we've been talking about that for a while, it has a distance of 128 picometers, and the distance between the nuclei is its picometers. So if you see in like the little graph, the like 100 mark, slightly above that would be like the 128-ish, and that's where like you would find the visual version of the distance for ozone. Then bond energies are the bond energy, or yeah, required to break 1 mole of bonds in like the gas phase. But I remember it better as the energy released when two particular atoms are bonded. And yeah, that's it for this lecture highlight. Make sure to take notes in chemistry. Try better for your midterms. Good luck.